Yeah, I'm Ben from University of Washington, and my research focuses on studying the coupled interaction of multiple agents in dynamic environments. So here's a photo that we're all sort of quite familiar with. In this example here, we have a machine interacting with a human. And oftentimes, the controller here is designed using either some sort of minimizing some objective. So optimal control, reinforcement learning, or any sort of optimization problems. So in this research, we're sort of asked the question, is there a missing puzzle piece here? And this puzzle piece might be the fact that the human is also learning. Because now we have multiple cost functions, this is fundamentally no longer a optimization problem, but is now a game in the game theoretic sense. And there's a lot of debate on what this cost function should be, but I think from last night's discussion, we've agreed upon that humans are trying to maximize chilling instead of minimizing costs. But jokes aside, in this problem, we're sort of studying sensory motor games, and two main questions that arise. What stationary policies might these coupled interactions converge to, and how do they converge to it? And just to quickly go over some notation, we're going to assume the policy and actions of the human to be UH, and the policy of the machine to be UM. And the joint action space is U. And each agent we have here is minimizing their own cost function with respect to their own choice variable. And the key distinction here is that the cost function is a function of both the actions of the human and the machine. So, of course, we're all rational, and in order to decrease the cost, we assume the model of gradient descent. So, at each iteration of the learning, we will take a step in the steepest gradient of our cost functions. So what this might look like, here we have just a single iteration of a discrete time update. And if your cost is nice and convex, we will converge to a local minimum. However, once we introduce a second agent with a second cost function, the dynamics of this learning process might end up being much richer because of the fact that the gradient that you're taking with respect to the cost function is no longer a gradient, no longer a derivative, but it's a partial derivative with respect to the costs. And to see why this might be the case, we take a dynamical systems perspective of this learning process where we can map the discrete time update with a continuous time dynamical system where the change in your policy parameters is related to some vector field omega. And by linearizing this vector field and looking at the eigenstructure of this Jacobian, we can start to make a couple of predictions of what we think this game dynamics might induce. And just to zoom in a little bit closer on what this Jacobian looks like, it sort of looks like a Hessian, where we have second derivatives on the block diagonals. But the difference here with the Hessian is that though the Hessian is symmetric, this Jacobian is not necessarily symmetric. And in fact, it can have eigenvalues that are imaginary, and it can also exhibit some counterintuitive behaviors. So just to sort of, using this mathematical model, we're hoping to make a couple of predictions, and as future work, perhaps develop some experiments to test these predictions. So first, to answer the what do they converge to question, agents might actually converge to local maxima. So in the first line here, we assume that the fixed point, the Jacobian at the fixed point ends up having positive block diagonals, indicating that the agents are on at their local minima. But there also exists fixed points where the Jacobian is stable, the fixed point is stable, but the cross-diagonal terms of the Jacobian have a negative, meaning that one agent might be at a local maxima. And the second prediction we have is that the agents might engage in sort of endless oscillating due to some imaginary values in the Jacobian. With that, I'd like to open up the floor for questions.
Can't they both win by not doing anything? Machine not doing anything, human not doing anything, then minimizing cost. So what's your constraint?
Maybe you can repeat the question.
Yeah, so what if the agents are not learning, are not doing anything? Will they converge to some
I mean,
stage?
machine stop working, humans stop working, that should be the minimum cost.
If you stop moving, you don't have any costs. Like, what's stopping from doing that?
So what is your given task to say?
Yeah, I guess in this mathematical formulation, we assume that the agents are continuously learning and always trying to optimize their own costs. So I don't know how to answer.
The cost given by these, I guess, landscapes that the game has sort of secret knowledge of, but the players don't themselves. Is that right?
Yeah, I guess it depends on the cost structure that you impose on the agents.
I guess the players have knowledge of the derivative, right?
The derivative.
Yeah.
Greg had a question.
I'm interested in the oscillatory behavior.
Mhm.
Can you say more about what features of each of the optimal landscapes of the agents look like and create that behavior? Where there's initial conditions?
So it all comes down to the off-diagonal terms of this Jacobian. So in zero-sum games, oftentimes you can decompose this Jacobian as a symmetric part and an asymmetric part. And the asymmetric part has the purely imaginary eigenvalues.
Ram and then Joe.
So why do you think that the people are rational?
Uh,
There are examples like in, for example, in traffic,
Yeah.
people do not necessarily behave in any rational fashion. So why do you assume that people are going to behave rationally?
Yeah, so I guess this is just a model, and models can be incorrect. So hopefully we're able to get some descriptive properties from this model to describe some agents' interactions. But none of this has been verified by experiments, so that's...
And just one more. So have you thought about the partially observable case? So in the instance where the human may not necessarily know or understand fully what the treadmill is trying to do, or the human in the loop optimization is trying to do.
Yeah, so currently we're assuming full information. The agents know their own cost function, but the actions of every agent. But definitely partial information is an interesting subject to study.
Joe Kusman.
In the work you're just showing, the agents are they're optimizing their own cost function, but are they also completely self-interested?
Yeah, they're
So there's no actual interact. So they're not only rational, they're blind to everything else going on.
yeah.
How
So
would you add interactivity then, which would be very common, right? Because humans are very collaborative.
yeah, so
we
we
will be affected by what the other three people are doing, right?
exactly. So we sort of assume the lack of trust and lack of communication amongst agents, but we also sort of formulate it as a feedback loop where you can observe the state of the system, and that's how you sort of try to communicate.
And also, those centers, that kind of thing, it's not structurally stable, so tiny changes in your model are going to obliterate that. Have you looked into that?
I'm not sure about the generic properties of the equilibria, but I think some of them are robust to perturbations and parameters. Maybe not the limit cycle case.
Those aren't limit cycles. The limit cycle would be an isolated periodic orbit.
Oh, I see what you mean. Yeah. This is kind of a toy example, sort of like rock, paper, scissors.
I think there was a question from Steve as Shayu was switching over, and then Max quickly.
I was just going to say, in this formulation, it seems that there are these two separate cost spaces that don't interact. But in the case of the person using a device, the landscape for the device is dependent on the person's coordination pattern, and that person's landscape is dependent on what the device is doing. So both landscapes are also constantly changing, right?
Yeah, exactly.
And okay, so that was one thing. And just the second part, real quick, is do most of these problems resolve if the time scale of adaptation to two systems are really different? Or in your case, you could say that step size of the gradient descent is really different in the two cases. Doesn't that resolve all of these issues?
So we studied non-uniform step sizes, and what that does is sort of warps the vector field so that the region of attractions for each stable points. So if you initialize in one point, you might end up in a different fixed point depending on the step sizes of each agent. But I'll be happy to show a bit of that work offline.
Max, did you have a last?
And whether or not that's an issue at all, the fact that these landscapes are interacting, constantly changing. You said exactly, and what's your response to Steve? But I'm wondering if you can expand on, like, if that's not a problem, like that's what you're assuming from the beginning, or whether or not that actually inherently changes the nature of what you're studying.
Yes, so the shape of your cost that one agent sees is dependent on the action that the other agent takes. So if you, or the policy parameters that the other agents have. So that's what sort of makes it different than an optimization problem, because yeah, like the local curvature of your cost function just changes just depending on what the other agent is doing.
Okay.